Deep beneath the ocean surface, boiling hydrothermal vents unleash toxic chemicals that should instantly kill all known biological entities, yet thriving colonies of alien-like microbes defy every law of nature. Welcome to the astonishing realm of extremophiles, Earth's most resilient organisms that rewrite the very definition of habitability and prove that life finds a remarkable way in absolute nightmares. For decades, science assumed life required warm temperatures, gentle sunlight, and abundant water, but extremophiles shattered this comfortable paradigm by flourishing in conditions once considered entirely lethal. To understand these incredible microscopic survivors, we must journey to the most hostile corners of our planet, starting with the crushing darkness of deep ocean trenches. Hydrothermal vents pump out water heated to over 400 degrees Celsius, yet these chimneys teem with bacteria that convert toxic hydrogen sulfide into living organic matter. Instead of relying on solar energy like plants on the surface, these vent microbes use chemosynthesis, harvesting raw chemical energy from Earth's violent geological core to survive. The immense hydrostatic pressure at these depths would instantly crush standard biological cells, yet piezophiles have evolved rigid proteins and flexible cell membranes to thrive there. Leaving the boiling ocean floor behind, our planetary survey now shifts toward the opposite extreme, traveling to the freezing, windswept expanse of the Antarctic ice sheet. Buried beneath kilometers of solid ice, pitch-black subglacial lakes trap liquid water in permanent sub-zero temperatures, forming isolated ecosystems untouched by the sun for millions of years. Psychrophiles are masters of cold adaptation, producing specialized biological antifreeze compounds that prevent ice crystals from forming and shredding their delicate internal cellular machinery. To survive the bitter cold and scarce nutrients, these frozen microbes slow their metabolic rates to a crawl, operating on microscopic amounts of energy over centuries. Some dormant psychrophiles can remain in stasis for immense periods, awakening instantly when environmental conditions shift just enough to allow basic cellular replication to resume. Leaving the icy poles, our expedition investigates environments so acidic they can dissolve iron nails within hours, yet certain specialized microbes call these burning waters home. Acidophiles thrive in sulfuric acid pools around volcanic craters, maintaining an internal neutral pH while swimming in an exterior bath that would melt human skin. The secret to acidophile survival lies in incredibly efficient membrane proton pumps that constantly eject invading hydrogen ions faster than they can penetrate the cellular interior. These hardy acid-loving organisms are not just biological curiosities. Industries now harness them for biomining, using microbes to extract precious metals from low-grade ore deposits. Moving beyond chemical corrosion, we encounter an even more terrifying threat: ionizing radiation environments capable of shredding DNA strands into microscopic molecular confetti. Meet Deinococcus radiodurans, nicknamed Conan the bacterium, an organism capable of surviving radiation doses thousands of times higher than what would instantly kill a human being. When radiation shatters the genome of Conan the bacterium into hundreds of random pieces, cellular repair proteins meticulously reassemble the entire genetic code within hours. Remarkably, these radiation-resistant microbes can even thrive inside spent nuclear fuel storage pools, feeding on organic compounds while bathed in intense, glowing blue Cherenkov radiation. From radioactive depths, our journey takes us to the blistering, hyper-arid expanse of the Atacama Desert, where rainfall can be measured in decades rather than seasons. Parts of the Atacama are so devoid of moisture that soil bacteria must extract microscopic traces of water vapor directly from morning fog rolling in from the Pacific. To escape the searing ultraviolet radiation and relentless drying winds, endolithic microbes burrow deep inside solid translucent rocks, living out their lives in interior mineral cracks. Life in the desert requires extreme miniaturization. These cells shrink their volume to conserve every available atom of water and maintain metabolic function under severe drought. Halophiles take refuge in thick salt crusts of evaporating hypersaline lakes, where osmotic pressure should rapidly rupture cell walls by sucking out all internal moisture. To prevent internal dehydration, halophiles pump high concentrations of potassium ions into their cytoplasm. balancing the external osmotic pressure and maintaining stable cellular chemistry. Shifting from salty hyper-environments to caustic alkaline soda lakes, we find organisms that thrive in water as soapy and basic as household ammonia. While most life uses protons to drive cellular motors, alkalophiles utilize sodium ions instead, turning the caustic soda environment into an energy-generating powerhouse. Beyond surface extremes, an immense shadow biosphere exists deep underground, where microbes inhabit rock fractures kilometers beneath the continental crust. Lacking any sunlight, these deep subterranean microbes feed on hydrogen produced by the natural radioactive decay of surrounding uranium and thorium-bearing rocks. The astonishing adaptability of Earth's extremophiles fundamentally alters our search for extraterrestrial life, proving that habitable zones in the cosmos are much wider than previously imagined. Mars was once a warm, wet planet with rivers, lakes, and subsurface hydrothermal systems, offering conditions remarkably similar to early Earth where extremophiles first evolved. Although the Martian surface is now cold, dry, and bombarded by cosmic radiation, liquid brine pools and protected hydrothermal niches may still exist deep underground. Jupiter's icy moon Europa harbors a vast global liquid water ocean locked beneath a thick shell of ice, warmed by powerful tidal gravitational forces from Jupiter. Scientific models suggest that Europa's seafloor features active hydrothermal vent systems, providing the exact same chemical energy inputs that sustain deep-sea extremophiles on Earth. Saturn's icy moon Enceladus takes astrobiology a step further, actively shooting plumes of water vapor, salts, and organic molecules straight out into space through crustal fissures. Future spacecraft will not even need to land on Enceladus. They can fly directly through these active eruption plumes to collect and analyze alien microbial biosignatures. Inside the laboratory, mass spectrometer data from simulated plume experiments help researchers identify specific amino acid chains and lipid structures unique to biological processes. Even Saturn's giant moon Titan, with its lakes of liquid methane and frigid hydrocarbon rain, challenges our assumptions by hosting potential exotic chemistries we are only beginning to understand. Astrobiologists theorize that theoretical non-water-based organisms could utilize liquid methane as a solvent, opening up radical new pathways for life in the outer solar system. Despite vast differences in environment, all known life on Earth shares a universal genetic code, suggesting that any life originating elsewhere in the cosmos might share similar foundational building blocks. Some scientists champion panspermia, the compelling hypothesis that resilient extremophile microbes could travel between star systems safely shielded inside rocky meteorite debris. Experiments simulating violent asteroid impacts prove that certain hardened bacterial spores can survive the crushing shockwaves and scorching temperatures of planetary ejection. When factoring in the sheer ubiquity of extremophiles on Earth and the trillions of potential water-bearing worlds in our galaxy, the mathematical probability of alien life skyrockets. Next-generation space telescopes are now powerful enough to scan the atmospheres of distant exoplanets for chemical imbalance markers, such as oxygen and methane coexisting. When starlight filters through an exoplanet's atmosphere, specialized spectrometers decode the spectral fingerprints of atmospheric gases, hunting for signs of biological activity. Back on Earth, researchers are using extremophile proteins to engineer synthetic biological systems capable of manufacturing biofuels and medicines under extreme industrial conditions. Extremophilic enzymes, known as extremozymes, maintain structural stability at high temperatures, revolutionizing molecular biology PCR testing and genetic sequencing worldwide. Studying extremophiles offers a humbling perspective on our own existence, reminding us that life is not a fragile accident, but an intensely stubborn cosmic imperative. Every extremophile species represents an evolutionary masterclass in survival, having tested and perfected genetic solutions to environmental hurdles over billions of years. Understanding how these hardy organisms cope with extreme environmental stress also provides critical insights into how Earth's ecosystems might adapt to rapid climate shifts. As drilling technology advances, we continue to push deeper into Earth's crust, discovering new metabolic pathways and bizarre microbial communities hidden away in rock. These microscopic guardians of tenacity remind us that wherever liquid water, energy sources, and basic chemical nutrients coexist in the universe, life will find a way. When future robotic explorers finally melt through the icy crusts of Europa and Enceladus, they may confirm what extremophiles on Earth have whispered for generations. We are standing on the precipice of a profound scientific revolution, one that will transform humanity from an isolated speck into citizens of a living, breathing cosmos. The quest to understand extremophiles is ultimately a quest to understand ourselves, charting our cosmic origins and our permanent connection to the vast wonder of the universe. From boiling hydrothermal vents to freezing Antarctic ice, these tiny survivors carry the genetic blueprint for endurance, resilience, and the eternal spark of creation itself. As we gaze out into the dark expanse of space, we carry with us the unwavering proof that life is remarkably tough, adaptable, and destined to explore the stars. Earth's extremophiles have forever changed our understanding of biology, transforming hostile nightmares into cradles of possibility and guiding our search for alien life in the cosmos. The universe is waiting, and the answers to our greatest existential questions are hidden in the most unexpected places, guarded by the most resilient organisms ever created. Thank you for joining this extraordinary scientific journey across Earth's most extreme frontiers. To explore more mysteries of the universe, subscribe to the Astrobiology Lab.